Hi everybody. I see no signal at all. Nothing on the screen. Нет сигнала. На экране нет сигнала.
Давайте пока начните рассказывать, я просто поставлю сюда ноутбук, на котором будет чат трансляции.
Ну, мне-то не нужна трансляция. Главное, чтобы там шел сигнал. Там звук идет?
We can hear and see you, Professor.
Okay, good. Okay, good. So I can't see this screen, but if the signal is okay, then we start this lecture. We continue our discussion of ideal gas. And last time we derived an expression for kT in ideal gas, which is Boltzmann constant and absolute temperature. And we obtained that this is 2/3 epsilon, which is an average kinetic energy of molecules of ideal gas. So from here, we can immediately obtain that the average kinetic energy is 3, I would put it like this, kT/2. 3/2 kT. And this is certainly the average kinetic energy is mv²/2, the average squared average velocity of molecules. So as velocity v can be decomposed into its component vx, vy, and vz, then we can see that this is the sum of average kinetic energy related to the motion of molecules along x-axis plus kinetic energy average of molecular motion along y-axis plus kinetic energy of molecules according to the z component of velocity. And also all these components of velocity and corresponding components of kinetic energy are equal. These terms are equal to each other. So this is just 3 epsilon Ex, which is 3 mvx² average over 2. Looking at this formula, at this part and this expression, or this expression, we can write that the kinetic energy of motion along certain axis, like x-axis, is just kT/2. Boltzmann constant and absolute temperature over 2. This is very important result. It will be used many times in the course of physics because the motion of molecules along one axis is 1 degree of freedom of molecules. And molecules in ideal gas have 3 degrees of freedom if the gas is monatomic, that is, if molecules consist of single atom. If we consider such simple case, a molecule consists of single atom, then each atom may move along either x-axis or y-axis or z-axis. All the axes, all the directions are equivalent. There is no difference between different directions. So each direction is just a degree of freedom of a molecule. of a monatomic molecule, a degree of freedom. And 1 degree of freedom contains energy kT over 2. This is important thing, because sometimes you have 2 degrees of freedom and then the average energy will be kT. Sometimes you have 3 degrees of freedom and then average energy will be 3 times kT over 2. So, and sometimes you have more degrees of freedom. When the molecule consists of 2 atoms, there will be a degree of freedom of vibrational motion of atoms and also rotational motion of this molecule. So there will be more degrees of freedom than for a monatomic molecule. And each degree of freedom will contain this average energy. That is a classical result which will be used to analyze, will be used in molecular physics to analyze molecules containing many degrees of freedom, more than 3, more than just motion in 3 different directions, but also rotation and vibration. In this case, such molecules will have more than 3 degrees of freedom, and this formula will be very important. But from the very beginning, I have to warn you that this formula is classical, and in quantum physics, this formula sometimes fails. But you will learn about it when you will study quantum physics. So this is an important result. I want you to remember it and to keep it in mind for future studies. Now, also during the last lecture, I wrote on the blackboard something like this: 8 grams of oxygen. And while pointing at this figure, once I said 4 grams, and the second time I said 10 grams. It's ridiculous, right? It's funny slip of my tongue, because 8 grams is correct, and what I said, like 4 or 10, it was because I was thinking about something else when I was talking about this particular 8 grams of oxygen. Well, now we will solve some problems in ideal gas, applied to ideal gases. The first problem I would like to consider is 334. A gas that occupies a volume V1 equal to 1 liter at a pressure of P1, which is 1 atmosphere, expands isothermally to a volume of V2 equal to 2 liters. Then the pressure of the gas is halved at the same volume. So the second pressure will be the original pressure over 2. The pressure of the gas is halved at the same volume. As the volume is the same, it means that, oh no, that will better not be P. That is not P2, that is pressure in point 3, because this was the first pressure, and here at this volume there we had the second pressure. We don't know which is the pressure P2 is, we don't know. And pressure P3 is just the previous pressure P2 over 2. The pressure is halved. That is what is said in the statement of this problem. Next, the gas expands at a constant pressure to V4 equal 4 liters. Draw a diagram of P versus V and use it to determine the process in which the gas performs the greatest work. How does the temperature change? Okay, we have to draw a diagram of pressure versus volume. So this point corresponds to 0 volume and 0 pressure, which is like an imaginary state. But we will never go to this point. We will consider some real pressures and real volumes, which may be depicted on this plane. So the first volume was V1, 1 liter at first. That was V1, 1 liter. And at this volume, the pressure was 1 atmosphere, P1. So there was some pressure, P1, and we know that that was 1 atmosphere. So the original state of the gas is characterized by this point on the PV diagram. Some initial pressure versus initial volume. And we have initial state of this ideal gas. What happens then? The gas then expands isothermally to a volume of V2, 2 liters. So the second volume, V2, is 2 liters, is twice the original volume, because the original was 1 liter, this is 2 liters. And we know it says that the gas expands isothermally. What does it mean, isothermally? It means that in the gas law, well, like this, temperature is constant. And if temperature is constant, then this expression shall be constant. Isothermal process isothermal means that the temperature is constant. It does not change. So if the product of pressure and volume remains constant and volume is increased twice, then the pressure should decrease. So the next pressure should be 2 times smaller than the original pressure, because the volume increased 2 times and pressure increased. So this was the first state, and this is the second state, and the gas state was changed from point 1 to point 2. And this is the next pressure, P2 in point 2. If the volume increased 2 times, then the pressure decreased 2 times. Because in this process, PV is constant. Isothermal process. What next? Next, the pressure of the gas is halved at the same volume. At the same volume, that is, at volume V2, which does not change in this process, the pressure is halved. It becomes 2 times smaller. So the next pressure will be P3, which becomes 2 times smaller than the original pressure. This is the middle of this section. This process is called isochorus. This process is performed at constant volume, as the problem statement gives the condition constant volume, and such process is called isochorus. This is an isochorus process, and this is an isochore. This curve is called isochore, and the process is isochorus. So this curve similarly is isotherm, and the process is isothermal. And then finally, the gas expands at a constant pressure to final volume of 4 liters. Final volume V3, which is given V4, which is 4 liters, twice the volume, twice the original volume in V2. And the process is at constant pressure. The pressure is constant. It means that it doesn't change. It was P3 and it remains P3 all through the process. So the pressure doesn't change. It means that the process is depicted by a line parallel to the horizontal axis and perpendicular to the axis of pressures. So the final state will be here. That is point 4 and that is point 3. And volume 3 equals volume 2 by the statement of the problem. That is, we have drawn a diagram of pressure versus volume, and now we will use this diagram to determine what does it say? We have to determine the process in which the gas performs the greatest work, the largest work. Which section corresponds to the largest work performed by gas? But before we proceed with the work, I would just introduce another term. So this process, which goes on at constant pressure, is called isobaric process. Isobaric process, and the curve is called isobar. That is such process when pressure is constant. This is isobar. Now we have to talk about a little bit about the work performed by a gas, because in this problem we have to find such a section on this curve, such a process during which largest work was performed. So we have to be sure that we understand what does it mean, the work performed by a gas. Imagine a gas in a cylinder under a piston, and the piston as usually can move up and down freely without friction, and the gas is here. So gas molecules move chaotically and they hit the piston and are reflected and rebounced, and therefore they impinge some momentum to the piston, and so the gas acts with some force on the piston. And we know that the force is related to pressure, and the pressure of the gas here is just the force with which the gas acts on the piston divided by the area of the piston. The area. This area. Therefore, the force is equal to pressure times area. And if the gas expands, then the piston will go up a little bit to a new position, so that it will shift by, say, delta L, by distance delta L. We can see this slow motion of this piston. It will go up by the distance delta L because the gas is expanding. If delta L is small, then the volume of the gas changes just by a small amount. And so we can consider during this process pressure to be constant. Pressure doesn't change considerably. And therefore we have some force with which gas acts on the piston and displacement. And for this reason, a work delta L some amount of work is performed, which is the force times delta L by definition of work. And force is P as pressure area, delta L. And now we note that S delta L, this area times delta L, is the volume delta V, the change in volume occupied by the gas. So this is pressure delta V, the change in volume. So we have derived an important formula showing that if the gas is expanding and its volume is increasing, then this gas performs some work. Delta A work equals pressure times the change in volume. What is P delta V on this diagram, where we have pressure shown along the vertical axis and volume V along horizontal axis? Graphically, it's obvious that pressure, any pressure at any volume, for example, in this point, we have some pressure and some volume, and if volume has changed by delta V, then delta V will be here, and pressure will be here. And so pressure times delta V will be the area of this rectangular figure, of this rectangle. So the work produced by the gas when the gas is expanding equals the area under the curve on the diagram, on the PV diagram. The work performed by gas can easily be depicted as the area under the curve on PV diagram. So the work performed during this process from point 3 to point 4 will be depicted by the total area of this rectangle. And the work performed during process 2 to 3 will be 0, because 0 area corresponds to this very, very narrow, infinitely narrow rectangle, infinitely narrow figure. If point 2 is above point 3, just above it, just along vertical line, then this figure has 0 area. And so the work performed during this process is 0. The work performed by the gas is 0 because the volume doesn't change in this process. And the work performed in process 1, 2 will be characterized by the area of this figure. And just looking at the picture, we can conclude that the work performed during process 1, 2, this work during process 1, 2, seems to be larger than the work performed during process 3, 4. So the answer to this problem will be most probably this one. A12 is larger than A34. Well, if the original pressure was 1 atmosphere, if I'm not mistaken, yes, original pressure was 1 atmosphere. So this is pressure 1 atmosphere. Then this pressure will be just half the atmosphere. Then this pressure will be, pressure 3 will be 1/4, 25% of atmosphere. And this change of volume is from 1 liter to 2 liters, so this is 1 liter. And this change of volume is given to us as 2 liters. So the area here will be the product of 2 liters by 1/4. So this work, A34, equals 2 liters multiplied by 1/4. So that will be 1/2. Some arbitrary units. It should be joules. The energy and work is measured in joules in the international system. But here it will not be joules because we use some unit like liter, which does not coincide with meter cubic. It's much less, 1,000 times less. So what we obtain here is not joules, but some arbitrary unit which we don't have even to discuss. So, and the work produced on the work contained, or the area contained in this rectangle, will be equal to 1 liter times 1 liter times this height, which is 1/2. So 1 liter times 1/2, the work produced here will be 1/2. So we obtain that the area of this rectangle is equal to the area of this rectangle. Therefore, the total work, total area of this figure is surely larger than the area of this rectangle by this top figure above the rectangular figure. So this square equals this area of this rectangle equals to this area. So we were absolutely correct when we concluded that the work performed during process 1-2 is the largest work in this total 3 processes with the gas. Next, we will consider problem number 329. Well, what if I move to this part of the blackboard? Problem number 329. A cylinder closed at both ends is separated into 2 equal parts. Let's draw a figure. A cylinder closed at 2 ends, so this end and this end are closed, and there is a piston in the center of the cylinder. And it says that the cylinder is separated into 2 equal parts, and each part has the length of 42 centimeters. 42 centimeters. Each part is 42. And the piston is impermeable to heat, so heat transfer is impossible through the piston. It's heat insulating piston. Both parts contain the same mass of gas, so the same mass here and here. At a temperature of 27 degrees Celsius. 27 degrees Celsius. So the temperature is the same, I would put it like T capital, which is absolute temperature, and lowercase t is usually used to denote Celsius temperature. The connection between temperature in kelvins and temperature in Celsius degrees, well, in general connection is what? When Celsius temperature equals 0, for Kelvin temperature this is not 0, this is 273 degrees. So if Celsius temperature is 0, Kelvin temperature is 273. If Celsius temperature is larger than 0, then accordingly you can calculate the absolute temperature, which is measured in Kelvin. So the absolute temperature corresponding to 27 degrees will be just 300 degrees Kelvin. If this is T1 corresponding to 27 degrees, then the sum will be 300 kelvins. Also, it says that, well, the same masses and the same temperature in both parts of this cylinder. And the pressure is the same. The pressure, initial pressure is given as 1 atmosphere. So the pressure of gas here and pressure of gas here is the same. How much should the gas be heated in one part of the cylinder to shift the piston by 2 centimeters? So we have to heat, we want to heat. The problem says that we heat one part of the cylinder, so we heat it, we put some amount of heat energy, delta Q, and the temperature here will rise in this part, in the left part of this cylinder. And how much should the gas be heated? It means that we have to find the final temperature here. That's the left part of the cylinder. So after we have heated the gas, it says that the piston will shift a little bit from the center. It will go to a new position, and it will shift by 2 centimeters, according to the statement of this problem. The piston will shift by 2 centimeters because we have heated this left part of the cylinder, the gas in this part of the cylinder. So this part will have the same mass. The mass is not lost, but some new temperature, which we have to find. And certainly some new pressure will be here. New pressure. Well, P1 probably, yeah. The new pressure. The original pressure was P, and then after heating, the pressure here will be P1. How much should the gas be heated? We have to find the final temperature in one part, in this left part of the cylinder, to shift the piston by 2 centimeters. Find the pressure P of the gas after shifting of the piston. Find the pressure P1. So we have to find P1 also. If in the right part of the cylinder the gas had mass m, then this mass is not lost in the process, it remains the same. But temperature will be different. We don't know what temperature will be here. It will be different. And it will not coincide with the temperature T1, because the piston is impermeable to heat. So there is no heat transfer through the piston. Therefore, the temperature in the right part and the right-hand part of this cylinder will differ from the temperature in the left part of the cylinder. And the pressure here will be actually the same as the pressure in the left part. So the pressure will be P1 anyway, because the piston moves freely without hindrance, and it moves so that pressure is balanced from both sides of the piston. The pressure must be the same. Such is the property of piston, which moves freely and stops just to balance the two pressures. So, how can we solve this problem? Surely we must use an equation of an ideal gas, which is PV equal, as we are given mass here, we can use this form of equation of ideal gas. The mass of the gas divided by the molar mass, the mole. How many grams consist in 1 mole of this gas? And then universal gas constant and absolute temperature. So this equation describes the state of the gas in any vessel, be it the left-hand side or the right-hand side of this cylinder. So for the left-hand side and for the right-hand side, we will use the same equation. Temperature is the same here, pressure is the same, mass of gas is the same as given in the problem. So pressure is the same for both parts and volume is the same originally, because the original position of piston was in the center of the cylinder and these two lengths were equal to 42 centimeters. So volume is the same originally and the mass is the same also. The mass is the same and temperature was the same. All the same, all quantities here in this equation are equal for both parts of the cylinder. Therefore, we may conclude that the molar mass of the gas in the left side and in the right side is the same. Therefore, most probably this is the same gas here and here, which is not given in the problem, but we may conclude, as all the quantities here are equal, then the mu is also the same in both parts, and therefore if two gases here have the same molar mass, then most probably this is the same gas. What changes after we have heated the gas? We supplied some heat to this part of the gas. We increased the temperature. What changes? We know that the new volume is defined by the shift of the piston. So if the original length was 42 centimeters, then after shifting the piston by 2 centimeters, it will be 44 centimeters here, and it will be just 40 centimeters here. So the volumes changed and temperatures changed, but pressure will be some new pressure P1, but the same pressure in both parts, and the mass remains the same, certainly. So we may write the gas equation for both parts of this gas. For the first part, we have new pressure P1, which establishes after the gas was heated, and new volume, we know this volume, how it increased, is the same mass, the same molar mass, the same mole and gas constant, and new temperature T1. That is for the left part of the cylinder. For the right part of the cylinder, we will have the same pressure. The pressure is the same, I explained it, because this piston can move freely here and it stops at the position to balance the two pressures. The same pressure in the right-hand side gas. Different volume V2, which differs from the volume V1 because the piston was moved to the right. And the same mass, the same molar mass, gas constant, and some new temperature. We don't know what temperature will be here. The temperature in the right part of the cylinder will not coincide with the temperature in the left part of the cylinder, because we increased the temperature in the left part, and the piston is impermeable to heat, so the heat energy from the left part will not go to the right part, and so temperatures will be different. So, what if we divide one equation by another equation? We will obtain, something will happen, something will cancel here. If we divide this expression by this expression, pressure will cancel, P1 and P1, and we will have V1 over V2. Then mass over mu will cancel, universal gas constant will cancel, and we will have T1 by T2 so, and this can easily be calculated because we actually know the volumes. As the cross-section of cylinder is the same and the volume is the cross-section, this area times 44 centimeters here, and the same cross-section here times 40 centimeters, then the ratio of the two volumes will be known. It will be like 44 centimeters over 40 centimeters. 44 over 40. So that will be, after dividing by 4, 11 over 10. Well, does it say anything else? A cylinder closed at both ends. I've forgotten the statement. A cylinder closed at both ends is separated into two equal parts. That's we know. By a piston impermeable to heat. Both parts contain the same masses of gas at a given temperature. Yes, so we know the initial temperature. How much should the gas be heated in one part of the cylinder to shift the piston by 2 centimeters? Find the pressure P of the gas after shifting the piston. Well, this problem, well, somehow it's not actually mentioned in the statement of the problem. It's not mentioned, but it's very important, by the way. It's very important, they should have mentioned it, that the temperature of the gas in the right side of the cylinder does not change during this process. Actually, this problem implies that the temperature is the same. So T2 equals the initial temperature. T2, final temperature here, equals the initial temperature. So that the process with the gas in this right part of the cylinder is isothermal. Isothermal, it's compressed under constant temperature. Surprisingly, nothing is said about it in the problem statement. They should have mentioned it, that the process here in the right-hand side is isothermal. Well, it's not obvious anyway. It's not obvious because nothing is said about the walls of this cylinder here. Either the walls are impermeable to heat, or the walls can freely allow the heat energy to go to and fro. Either the temperature is sustained constant or not. Nothing is said about it in the statement of the problem. Well, this is not good for the problem. Actually, it should have stated something about the temperature. So if the temperature has not changed, which is implied in this problem, then we know the temperature T2, and therefore T2 is the same as the initial temperature, and we know the initial temperature. This is 300 Kelvin. If we know T2, then we can easily find from here T1. T1 is the initial temperature T, which coincides with T2, times 11 over 10. So initial temperature is 300 Kelvin, 300 Kelvin, 11 over 10. So the answer will be 330 Kelvin. That is the final temperature, T1, for the gas here. So we have found the final temperature, and the initial temperature was 300. So we know that we have to increase the temperature here by 30 degrees. The temperature difference is 30 degrees. When we heated the right-hand side part of this cylinder, the temperature must rise by 30 degrees. So now we can calculate, what do we need else? We need to calculate pressure, P1. Pressure P1 can probably be calculated from here. So P1 will be equal to, oh no, just a little bit, just wait a bit. So the gas here in this part experiences an isothermal process when the temperature is constant. For isothermal process, we know that if the temperature is constant, then PV is constant. And so the initial temperature, the initial pressure is given 1 atmosphere, and initial volume is V. Initial volume is V1. Initial volume is is proportional to 42 centimeters. Will equal to initial pressure here, and initial volume will be proportional to final pressure. Here will be equal to final pressure times final volume. Final volume here is V2. And pressure is the same in the second part or in the first part of the cylinder. Pressure is the same. So it doesn't matter what pressure we use, P1 or P2, it's the same. So that final pressure P1 of gas in the cylinder after heating will be initial pressure V over V2. Initial pressure is known, it's 1 atmosphere, it's given in the problem. And now we have to find the ratio of volumes, the initial volume here, 42, and the final volume here is 40. It's 42 related to 40, because volume is the cross-section area S times L, the height of this cylinder. And the cross-section area doesn't change, it remains the same. So the ratio of two volumes will be the initial height, 42 centimeters, divided by final height, which is 40 centimeters. So 1 atmosphere times 21 over 20, that will be 1.05 atmosphere. That is the final pressure P1, and we calculated it for the right part of the gas, right part of the cylinder. But pressure in the left part will be the same. So we have found the answer to this problem. We have found the final pressure of gas in both parts of the cylinder. Well, I find out that sometimes they formulate the problems, the formulation is not ideal. They sometimes miss one or another thing in a problem. And the next problem we will consider will be a 335. Probably this one. Yes, 335. Well, problem 335 says a cyclic process depicted on a VT diagram, that is a volume temperature diagram, shown in the figure. And I will have to copy this figure for you from the collection of problems. So we have volume versus temperature diagram. And the process is this. At first, the gas expands, increasing its volume from point 1 to point 2. And this line goes through the origin of coordinates. So this is the first process, 1, 2, and then the process is depicted by this line. The temperature of the gas is diminished, and then the gas returns to the original point 1. At constant temperature, the volume is decreased at constant temperature. Such is the diagram of the cycle. And it says that a cyclic diagram is performed with a certain amount of an ideal gas. Show the same process on a PV diagram. So we have to show the same process, the same cyclic process, on the diagram of pressure versus volume. Show the same process on a PV diagram and indicate the stages when the gas received and when it released heat. It said rejected heat. I don't like this word. It's better to say to release heat than to reject heat. It's better to say to release. So on some parts of this process, the gas received heat, energy from external bodies, and on other parts of this process, the gas released heat to external bodies. But first, we have to find out where the gas was heated, where the gas released heat, and where the heat energy increased and where the heat energy decreased. And also we have to draw this diagram, to draw the process, the diagram of this process in PV axis, in pressure versus volume axis. Okay, so the first point here corresponds to some volume and some temperature. Initial temperature P, initial temperature T1, and initial volume. And then volume increases to point 2 and temperature increases to some temperature T2. But on this process, volume is directly proportional to temperature. If we remember the gas law, we may take it for 1 mole. It doesn't matter because the problem doesn't specify how much gas we have. We are given some amount of mass, some amount of ideal gas, it says. So we may assume that we have just 1 mole of gas. It doesn't matter how much gas is there. So the equation of an ideal gas will be written like this. And if volume changes directly proportional to temperature, it means that pressure is constant. It means that pressure is constant during this process. So pressure is constant. How do we call such processes with constant pressure? We call it isobaric processes. So if pressure is constant, then we have to choose some initial point here on this diagram. Where is this point depends on the units of measurement and the scale along each of the axes. We don't know the scale and we don't specify the units, so we choose arbitrarily the initial point. It may be anywhere. We choose the initial point, and we know that the process from point 1 to point 2 was under constant pressure, and the volume increased from V1 to V2. The volume increased. So the increase in volume under constant pressure means that pressure was not changed, and the corresponding process shall be depicted by a line horizontal to the volume axis. So that is the process 1, 2 shown in PV axis, and pressure versus volume. Pressure is constant. We know about it. Why do we know? Because of the gas law. If volume changes directly proportional to temperature, then it's obvious that pressure should be constant. That is why this process is isobaric. And that is why if pressure is constant, then this process is depicted by this line, horizontal section of line parallel to the volume axis. So this is the first process shown on PV diagram. The second process is from point 2 to point 3, which goes under constant volume. The volume remains constant, and the temperature decreases. If the volume is constant, then we have to move along vertical axis. The volume should not change. It should remain the same. But if the temperature is decreased, then it's obvious. Look here. The volume now is constant. And the temperature should decrease from point 2 to point 3. The temperature should go here. The temperature goes down. So if the temperature decreases and volume is constant, then the pressure also decreases. So here, under constant volume, we have to go to a lower pressure. The pressure should decrease to some point 3. So this is point 3. The pressure should decrease. Original pressure was here, and final pressure will be here. All our consideration is based on application of universal gas law. We just have to figure out which quantity remains constant in every process, and then it's obvious how to draw the curve corresponding to a particular process. And the last process here is from point 3 to point 1, which is isothermal process, which goes under constant temperature. Temperature does not change here. Temperature is constant, T1. So this is isothermal process, and the volume is diminished. And again, if temperature is constant, then during this process, PV is constant. If temperature is constant, then PV is constant. The product of pressure and volume. The product of pressure and volume here on this diagram is constant, and such a curve is a hyperbola. And on this curve, the product of pressure times volume remains constant. The volume decreases, the pressure increases. So this is a part of a hyperbola corresponding to isothermal process. Isothermal, this is not a direct line. This is a curve, a hyperbola. And now we have to figure out what amount of heat is supplied to the gas. What does it say? Show the same process and indicate the stages when the gas received heat energy and when the gas lost some heat energy, or radiated heat, or released heat to the surrounding bodies. So we have to indicate either here or here where we have to supply the gas with some heat energy and where the gas will release some heat energy to the surrounding bodies. Well, heat energy is, we usually denote heat energy as some amount of heat energy as delta Q. If we supply some heat energy to a gas, let's do it this way. We have a cylinder with a piston, as usually, and here is some gas, and here is some volume and some pressure of gas and some temperature. So if we supply heat energy to the gas, what happens? Molecules begin to move faster, and the pressure of the gas increases due to the increase of temperature. And so the piston may go up a little bit if we allow it to go up. So when we supply some heat energy, it surely goes to increase, in general case, it goes to increase the temperature, that is to increase the internal energy of the gas. It goes to the increase of internal energy, that is the internal energy. Internal energy of the gas, which is characterized by the intensity of motion of its molecules. The more intensive motion, the faster the speed of motion, the more internal energy will be contained in this gas. So when we heat the gas, we increase the internal energy. And in general case, if the piston is not fixed, if we allow this piston to go up a little bit, then due to this shift in coordinate, the piston will produce some work. Actually, the gas will push the piston, and so the gas will expand and produce some work. So also the gas may produce some work due to heating, due to supply of external heat energy. So this is the supply of external heat energy to the gas, and this is the increase of internal energy, and this is the work produced by the gas. What we have written here is just a law of conservation of energy. Law of conservation of energy applied to an ideal gas. Actually, this law is a fundamental formula for thermodynamics, and it's called the first law of thermodynamics. That's just a law of conservation of energy. So the internal energy is, for an ideal gas, this first term is proportional to the change in temperature. If temperature rises, the change in temperature is positive, then the internal energy increases. It's also delta U is positive. And the work produced is directly proportional to the change in volume. So we know that the work produced is pressure times delta V, the change of volume. If the gas is expanding, then the change of volume is positive and the gas produces positive work. But sometimes the gas can be pressed and the volume will be decreased, and so delta V, the change in volume, will be negative. In this case, we say that the gas produces negative work. Actually, in this case, we produce some work on the gas by pushing the piston, by compressing the gas. External forces produce work, positive work on the gas, and the gas produces negative work, because the gas exerts pressure on the piston, and if piston goes down in the direction opposite to the force acting from the gas, then the force is opposite to the displacement, and force times displacement will be negative if the gas is compressed. So the work produced by the gas will be negative if its volume is diminished, and the work produced by the gas will be positive if its volume is increased. So that's enough understanding of the law of conservation of energy as applied to an ideal gas. That's quite enough to solve our problem. That's quite enough to understand where the gas is supplied by external energy and where the gas is releasing an external energy. So on the first process, what do we have here? The temperature of the gas increases while the gas moves from point 1 to point 2. The temperature obviously is increasing from T1 to T2. The temperature is increasing. It means that the internal energy is increasing. And also the volume is increasing here. The volume of the gas expands. Therefore, the work produced by gas is also positive. So on this part, on the first part of on the first process, we have to supply energy to the gas because its internal energy is increased with temperature, and also the gas produces some work. So on this portion, we supply some energy to the gas. On this section 1, 2, the energy is supplied to the gas. Some energy from external bodies. We have to heat the gas in order to produce this process, in order to perform this process from point 1 to point 2. Well, as far as the process 2 to 3 is concerned, what happens? The temperature is decreasing from high temperature to low temperature. The temperature is decreasing. So on this section 2, 3, internal energy is decreasing on this section. And the volume remains constant. If volume remains constant, then the change in volume is 0. So the work is not produced. The work produced by gas is 0 on the section 2, 3. So the only thing the gas does is decreases its internal energy on this process. If it's decreasing, then it has to release some internal energy and it has to give some energy to external bodies. So on the process 2, 3, the gas releases energy. What happens on the process 3 to 1? The temperature is the same. The temperature here is constant. Therefore, internal energy is constant. It doesn't change. As the temperature doesn't change, the internal energy doesn't change. But the volume is decreased. So the change in volume is negative. So the gas produces negative work. And it means that the gas releases some energy. Delta Q is negative when the gas releases energy, and delta Q is positive when we supply energy to the gas. So on this section of the process, the gas should release some energy to the outside bodies. So during this circular process, only on this horizontal, on the first part, 1 to 2, the gas obtains some energy. It's supplied with energy from external bodies. And on the other two sections, the gas releases energy to external bodies. That's as far as the energy flow is concerned. So we have a clear picture what happens with this gas, and we can depict all the processes in the VT diagram, in PV diagram, and also we may conclude when the energy received, when the energy was supplied to the gas, and when the gas released energy to the external bodies. That's all the solution of this problem. Well, we will have no time to consider any other problems. We know we have no time, and the only thing I have to say to you, don't forget to send me your solutions of the previous week, of the last week of mechanics. Don't forget to send me your solutions by the end of Sunday. And we come closer and closer to a written test, which will be most probably held next week. And I will inform you additionally about the time and conditions and time and procedure of conducting a written test. So, on this point, let's finish this lecture. Goodbye, everybody. Все, мы закончили. Останавливаем, все, да. Все, я не успею.